Good morning, students. In the previous video session, we have started the sound unit and we have learned about the stress, strain, normal stress, shearing stress, rolling stress. Today, we are going to have a new topic about Hooke's law. In 1994, Sir Robert Hooke, he verified the behavior of a spring or the behavior of plastic and elastic material, and he proposed a theory. He proposed a law which is called Hooke's law. Robert Hooke, his name is Robert Hooke. He proposed this Hooke's law, and he verified. He proposed this law by verifying the elastic behavior of plastic and the elastic material. For that, what he did means, he just and this law, what is this law means? He just said that he just proved that stress and strain are directly proportional to each other for small deformation. For a small deformation, stress and strain is directly proportional to each other. That is Hooke's law. It means, I'll show you. I have a stick here. When I am applying the force on this stick, now you can see the stick bends. Now the stick bends. So for this small deformation, I am applying now a very small force on this stick. That is what he said, for this small deformation. Not only this stick, just for example, I showed this stick. This rubber band spring and all. When you stretch this rubber band up, it extends somewhat, then what will happen? It will start to break. Also, the spring, you stretch up to some extent, what will happen? The spring will expand. Spring will elongate. After that, you know that the spring will not elongate. It will permanently what? It becomes a string. It becomes a string. So there is what Hooke said, Sir Robert Hooke said, stress and strain are directly proportional to each other for small deformation. For a small deformation, stress and strain are directly proportional to each other. This is what if you are applying less force on this plastic material, what it will, this stress produced on this stick and the strain, both what are directly proportional to each other. That is what it is said. Directly proportional means both nothing will happen. If you leave the force, it will come back to its original position. You see. Now I am applying a small force on this. Now it bends. When I am leaving that force, it comes back to its original position. It regains its original property. That is what Hooke's law. So he verified this by using a small experiment. For that, he just took a pan like this. He made an experimental arrangement. Okay. So this is what is experimental arrangement in page number 54. You can see this experiment, and here he made a ruler. Made a ruler and here a pointer. It's a pointer, a pen, here a loader. This is spring. So, for this experiment, what is used? A spring of length L, and it has a uniform cross-sectional area A. String length L, uniform cross-sectional area A. You know that uniform cross-sectional area means? What is the meaning of uniform cross-sectional area? Yeah, that is what you know the string. If you are taking a string of length L, this much string we are taking. Suppose I am taking this string, this much length I am taking. It has the same area. This much part, same area. That is what uniform cross-sectional area. Like that, a string is chosen of length L and the cross-sectional area again. And it is what stretched like a spring. It is stretched like a spring. Now, one of these stretched spring is attached to the point O, a fixed point O, and another one of this free end of this string which is attached by using a band and a point. What is the use of this point? Then what? Here there is a vernier scale used. So the pointer will show the reading when the string elongates or when the string expands. So here when we apply the load means what? 50 gram, 100 gram. So when we apply this 50 gram load or 100 gram load, what will happen? We are applying a force on, stretching force on that, stretching force F on this pen. So due to this stretching force, an elongation produced on the spring. Elongation, what will happen to the spring now? The spring will elongate. Its length will increase. When you are applying 50 gram, the spring expands little. When you apply 100 gram, the spring elongates little more. So that is what. So the stretching force because of the load. So the stretching force and the elongation produced on the spring is directly proportional for its length and inversely proportional for its cross-sectional area. For the original length, until this original length, what will happen? It is directly proportional. What? Force increase, you are putting the 50 gram, for that some extension. 100 gram, another some extension. So if you are drawing a graph, you will get a graph like this, a straight line graph. That is what for this original length, until some part, only for its original length, this thing, rubber band you are taking. You extend, you apply a stretching force on the rubber band, up to some extent it will expand, then it start to break. The same thing here, for its original length, what will happen? These both are directly proportional and it is inversely proportional to its cross-sectional area. When this spring is stretched more, its uniform cross-sectional area is changing. For example, this thing, rubber band you are stretching means some part its area will reduce and some part area will increase. So the uniform cross-sectional area is changing. So that is what it is saying. The force, stretching force and the elongation is inversely proportional to each other. So for its original length, both are directly proportional and inversely proportional to its cross-sectional area. So if you are drawing a graph, stretching force F on x-axis and extension, elongation delta L on y-axis, you will get a straight line graph. This graph passing through its origin. Now a small relation is there. This we have to prove from this graph F is equal to delta L. That is what slope. From this slope, force increase, elongation increase. Force increase, extension increase. Force increase, extension increase. So both are what? Both are equal. That is is what from the slope we are taking f is equal to delta x. Now multiply and divide by volume. We know that volume V is equal to area into length in equation 1. This you take equation 1. In that equation 1, you multiply and divide by volume. V is equal to air. So F equal to delta L into AL divided by AL. Now take this AL this side, F into AL equal to delta L into AL. Now just rearranging this equation, this A you keep it down, this L you bring it down, and this A you bring this side down. So F by this A will come here, F by A. Now A will come here, down. Now this A will go here. So delta L divided by into L by A. This L you bring down. Yeah. So just rearranging this equation. So we will get F by A equal to delta L by delta L into L by A. So you can rearrange and write this equation L by A into delta L by L. Now you can take this as a constant, proportionality constant. So F by A is directly proportional to delta L by L. This is what stress is proportional to strain for this slope. And for a small deformation, stress and strain are directly proportional to each other. So Hooke's law verified by using this small experiment. So this is what F by A means what? Stress. Delta L by L means strain. So stress is directly proportional to strain. That is what the Hooke's law. For a small deformation, stress and strain are directly proportional to each other. So this is also Hooke's law, and you can see in page number 54 just to go through that. And you have to learn this law. It is very important, 2-mark law. Hooke's law is for a small deformation, and the stress and strain are proportional to each other. First 3 lines, then just to go through that, go through this derivation. Now the next point, the next part is stress strain profile curve. Stress strain profile curve. This curve. So just giving a graph and saying that this point, until this point this will happen, and after that point something will happen for this behavior of plastic, behavior of elastic, all found out by using this curve. You know this thing, if you are taking a rubber band, if we stretch, if we apply the force on that until some point, you can see that it will not break, it will extend. Like you know this, if you are taking a ruler, this is a plastic ruler, if you are applying the force on this, until this, it will come back. Again, I am applying the force on this, what? It will break. It will break if I apply more force on this ruler. So if it is breaking means, what? That is the behavior of plastic. Suppose if it is an elastic ruler, until some extent what? It will not break. You can bend like anything. That is different behavior, elastic behavior. So based on this graph analyzation, by analyzing this graph, the behavior of elastic and the plastic is mentioned. That is what the stress strain curve it is saying. You can see, just to go through that. O until this point the OA graph is straight, then from the point A you can see the graph start to curve shape. So that is what now we are going to see until portion OA. Portion OA means what will happen? So this part stress and strain are directly proportional to each other. So portion OA means what? You can see straight line graph. Straight line graph means stress and strain both are directly proportional to each other until the point A. The point A is the limit of proportionality or proportional limit we can tell. So until the point A, Hooke's law is obeyed. What is Hooke's law? For small deformation, strain and stress is directly proportional to each other. So until the point A, Hooke's law is valid. Hooke's law is valid. We can apply the Hooke's law until this point A. Graph is straight line. Hooke said that same only. Stress and strain directly proportional to each other. Both should have extend at the same. So that is what until the point A, stress and strain are directly proportional to each other, and this point one name is there, limit of proportionality. After this point, Hooke's law is not valid. So that is what this point A is called as limit of proportionality. And next part AB. Portion AB, what will happen? Under the portion A is the point you can say limit of proportionality. Beyond that A, what will happen means Hooke's law is not valid. Stress and strain is not directly proportional to each other. Stress and strain are not proportional to each other. Maybe what force will increase. This stress is increasing, so it is not proportional to each other. Stress and strain both are equal, only we can tell that it is directly proportional to each other. Here stress becomes changing. So what is happening means beyond this point A, Hooke's law is not valid. And we can tell this point B is called as elastic limit. So until the point B, this is the thing. Until the point B, it will regain its original position. If you are applying the force, it bend. If I am leaving the force, it will regain its original position. So the point B is called the elastic limit. Beyond this B, this will not come back to its original point. That is what part BC. Portion BC. Strain increased more. So what will happen means beyond the point of B, stress increases and the wire will not regain its original length. That is what I said. Until the point B, up to the point B, B is the elastic limit, so up to the point B, it regains its original position. If I leave this force after the point B, it will not regain its original position. You can see, it will not regain, but until this point B, it come back to its original position. So this is what portion BC, then portion CD. You know one thing, BC is what? There also strain is more. Then what will happen? That is what the next portion CD portion strain is increasing more. Strain increase rapidly. So what will happen? If you remove the load also beyond this D point, if you remove the load its original position. Again you are applying the force up to the point E. From the point E it start to break. You can see here I am applying more force. Start to break. So it is a plastic behavior of this rule. It is a plastic behavior of this rule. So that is what last one, point E. So beyond the D is known as fracture point, and from the point D ultimate stress point, then E, point E, it is what it is called as breaking point or rupture point. You can fracture, broken. You see, until some extent it will come back, it regain its original position. Now it is plastic behavior, broken. That is what you can just go through that page number 54 and 55. This stress strain profile curve. You can just go through that. This Hooke's law you have to learn, that a 2-mark question, and this just go through that. It's not very important, but just go through that. Now I am going to tell about a very important question. Very important question. Modulus of elasticity. Modulus of elasticity or moduli of elasticity. This is very important question, 5-mark question in this unit. Very simple question. You have to write about the 3 modulus, 3 types of elastic modulus: Young's modulus, rigidity modulus, bulk modulus, third one is rigidity modulus. So Young's modulus, bulk modulus, rigidity modulus. Based on this Hooke's law, for each point we have gone through this graph and down. So now you know each point what will happen, and up to this slope we can tell rigidity modulus. So this slope we can tell what until this we can tell it is rigidity modulus of a wire. Suppose you are taking a sticker. So if stress and strain both are directly proportional to each other until that point, that is what the Young's modulus. So above that, it is elasticity behavior is changing. Based on that behavior, it is named as what bulk modulus and the rigidity modulus. So in that, first one is Young's modulus. Very important 5-mark question. Young's modulus. You have to just write the definition and the formula. 3 definition, 3 formula, 5 mark. Very simple. Rigidity modulus means ratio between tensile stress and the tensile strain. You know this tensile strain means, tensile stress means, you know. So Y is equal to tensile stress or compressive stress divided by tensile strain or compressive strain. So Y is equal to tensile strain stress. So F T by delta A T is called order. So tensile stress by tensile strain. You know this thing. This is what the Young's modulus. Sorry. Tensile strain, stress, tensile strain. sigma t by epsilon t, or we can write y is equal to sigma c by epsilon c. Tensile stress, tensile strain, compressive stress, compressive strain. And if you are taking this both the ratio, we will get what are Young's modulus values. So actually these values and all, Young's modulus calculation, rigidity modulus calculation, bulk modulus calculation, where it is useful means, suppose these engineers, civil engineers and all use this calculation, and they use the material for the construction and all, for building construction and all, how much strong it is, how much it bend, how much it lasts. These and all, these calculation and all made by using these modulus, Young's modulus, rigidity modulus and bulk modulus. So in the first one is Young's modulus. Young's modulus means what? Tensile stress, the ratio between this tensile stress to tensile strain, or compressive stress to compressive strain. So y is equal to sigma t by epsilon t, or sigma c by epsilon c. You can see in page number 55, Young's modulus. You can write about that. When a wire is stretched or compressed, the ratio between tensile stress and tensile strain is defined as Young's modulus. Then that regular table is there. That formula, equation 7.6. Then you have to write about the unit of what are the same unit as stress, strain has no unit of. Then second thing is bulk modulus in page number 56. You can see bulk modulus. Bulk modulus formula is what are? Volume stress, ratio between volume stress to volume strain. That is what bulk modulus. So K is equal to normal stress, or you can tell pressure. That is what to volume strain. This normal stress means what? Normal stress, what? Normal stress means F by delta A. F by delta A. That is what you can see in page number 56. Bulk modulus, it is defined as the volume stress to volume strain, and the formula normal stress or pressure by volume strain. Now normal strain. Normal stress means what? F by delta. This is what normal stress F by delta A is. F by A means what? Force by area is called pressure. So you can write this as pressure. Here delta A, so you can write down change in area is there. Delta A means change in area, so you can use change in pressure, delta C. So F by delta A. So bulk modulus means what? Ratio between volume stress to volume strain, and the formula is what? Normal strain or pressure means delta P volume strain. Volume strain means what formula? Volume strain is epsilon is equal to delta V by V. Now you can substitute these two in this formula. So bulk modulus K is equal to normal stress of pressure delta P divided by volume strain delta V by V. So volume bulk modulus finished. Then last modulus is rigidity modulus. Rigidity modulus. Rigidity modulus is shearing stress by shearing strain. Shearing stress by shearing strain or angular strain, you can see in page number 57 above the table, rigidity modulus or shear modulus. Rigidity modulus in textbook one mistake is there, you can correct the mistake. The definition is, in textbook it is given rigidity modulus is defined as the rigidity modulus or shear modulus. It is wrong, you can correct it, the definition. All of you listen carefully in page number 57, rigidity modulus definition is, it is defined as the rigidity modulus is defined as the ratio of shearing stress to shearing strain. Ratio between shearing stress to shearing strain. That is the definition. You can correct in your textbook. And it is given what are? Eta R is equal to, that is what are? Rigidity modulus. Shearing stress by shearing strain. Shearing stress means you know the formula. Sigma S is equal to tangential force by area. So sigma S is equal to F by area, and the shearing strain is equal to what? You know the formula, epsilon S is equal to X by H equal to theta. This is what angle strain. Now substitute these two in this formula. So eta R is equal to shearing stress Ft by delta T divided by X by H is equal to Ft by delta A by theta. So, if you are writing the definition with this formula, you will get a 5 mark, 3 definition plus 3 formula. So, very simple question. First, Young's modulus. Young's modulus means what? Young's modulus definition is what? Ratio between tensile, ratio between what? Tensile stress or compressive stress to tensile stress. Formula: Y is equal to sigma T by epsilon T, or Y is equal to sigma C by epsilon C. Now, bulk modulus. K is equal to what? Normal stress or pressure by volume strain. So the ratio between what are? Volume stress to volume strain. Volume stress will either be written as normal stress or pressure. So calculation. Normal stress is sigma n is equal to F1 divided by delta A. That we can write delta P, and here volume strain sigma epsilon V is equal to delta V by V. So, okay, substitute these two in this formula. So, K is equal to delta P by delta V by the rigidity modulus. It is defined as the ratio between shearing stress to shearing strain. Shearing stress is what? The tangential force by area. So, Ft by delta A, and this one epsilon S is equal to X by H, that is equal to theta. Angle strain you can tell, or shearing strain. Both you substitute here. You get a rigidity modulus. Page number, I think you have marked already. 55 Young's modulus, 56 bulk modulus, 57 rigidity modulus. With this formula you have to learn. You see here some values are given. Steel. What is the value? Bulk modulus, what is the value? And this is what the engineers used for the construction and all. And thank you all of you. Study this model of elasticity, Young's modulus, bulk modulus, rigidity modulus. Very important question from this unit. 5 mark question. You can expect in exam as well. So study well, prepare well. Thank you. Bye bye. See you.